Today I'm going to discuss protected mode. Previously we have seen how in real mode, classic DOS programming, any program could access any memory directly, modify some critical structures like interrupt tables and hook interrupts this way, and how any program could access any hardware directly through I/O ports. This obviously was not safe. You had to depend on all programs playing nice and cooperating with each other, and any single program could just break everything. It is possible for a DOS program to take over control of entire computer, and you could even launch another operating system this way, and there are people that are developing their own operating systems, hobby operating systems this way, that you can just test it by launching from DOS. And so, starting with Intel 286 processor, there was introduced a new mode, protected mode, that was designed to fix problems like the ones I just described. And we are going to start with protected mode of 286 processor. This was still a 16-bit processor, and starting from the very first implementation of protected mode should give us a better context and better understanding how protected mode evolved over time. I have this manual. You can find it on Wikipedia. It is linked in Wikipedia in the article about 286 processor. You may notice that at the time, in 1983, Intel was calling this architecture IAPX 286. This was a short-lived name, and by the time I was learning about Intel architectures and protected mode in the 90s, this name was already forgotten. So I only found out later that such name existed. Let me look out for something. So, how did 286 approach the problem of protection? And we will start with the problem of accessing any memory. So, in real mode, you had segment and offset. And segment was just a direct address in physical memory. Any segment, it was a 64 kilobyte window into physical memory, starting at address defined by the value of segment. Every next segment started on a paragraph, so difference of addresses of two consecutive segments was 16 bytes. So the segments were overlapping. For this reason, you could only address effectively 1 megabyte of memory. In case of 286, these simple segments were replaced by protected mode segments. Well, when you switch to protected mode, of course, because 286 still had real mode and then everything was as before. After you switch to protected mode, segments were defined in a special table, descriptor table. And each segment had individually assigned base address and additional attributes. This was something new. The attributes could be saying what the size of segment was. It could be a smaller window than 64K like before. Additional attributes could be that segment might be only readable or only executable, or readable and writable. And you could not, in this architecture, you cannot mix executable with writable. So this is about descriptor, but here we have selector. This is what replaced segment. This is what replaced the value that was put into segment register. So instead of just defining a basic physical address, here we have index into the descriptor table. We will be looking at the descriptor table later. A single bit, which is a table indicator, because there is global and local descriptor table. And requested privilege level, which indicates the privilege level of the user of this selector. We are going to analyze all this, but for now, let's prepare an environment for some testing. Since we are going to limit ourselves to 286 for now, then I would like to use FASMG, because with FASMG we can just limit ourselves to the selected instruction set with the right set of includes. Yeah. We need to set up some This is going to ensure that we can run Windows applications, console applications here in DOS, so FASMG. And we also need to set up include variable for FASMG. To use the CPU macros. Alright, let me restart this machine. Okay, variables are set. Passenger should be working. Great. Let's try to assemble one of our earlier programs. This time include instruction set. Setup extension of output file. Okay. Original 8086 processor had no push immediate. Just as a curiosity, some of the instructions that we may take for granted were introduced later in 196. Okay, this works. So, we have the tools ready. Let's start working on some 286 features. So, we want to set up protected mode of 286. Here we have what this descriptor looks like. Please note that Intel in documentation uses this way of showing memory as going upwards. The higher addresses are upwards on the page. This convention is may look a bit strange, because when we write down structures or just define data for assembly, we write it from up to down. And here we have memory going upwards. So when we write down these structures for a compiler or assembler, then we have to reverse the order visually. So this is in fact the first field of the structure, this is the second one, and this is the last one. And each of these fields is 16 bits. So 2 bytes. This is 1 byte, this is another. 8 bytes for everything. Well, I do not really know the reason for this convention. Every descriptor is 8 bytes. And when we look at Selector, once again, the index in Selector starts from the 4th bit. So this is, if we ignore the lower bits, this value is shifted 3 bits upwards. This is equivalent to multiplying by 8. And single descriptor in descriptor table is 8 bytes. So if we ignore the lower 3 bits, then the value of selector is in fact offset into descriptor table. And because descriptors start every 8 bytes, then of course the 3 lower bits have to be 0 for this to be a valid offset into a descriptor. And then these 3 bits have been reused for other purposes as a table indicator and privilege level indicator. So we can look at this as an offset into descriptor table. Or again, as often in the original, in early Intel architectures, we can look at this in octal system as a number that the lowest digit has other purposes, and the upper octal digits define index in descriptor table. So we have a few different ways of looking at this. This should become clear when we start writing some code. Let's go back to descriptor definition. So, due to this convention, the field at the bottom is the first field, and this is going to be the limit or the size of the segment. Limit is the address of the last valid byte of segment that is defined by such descriptor. Then comes base, 24-bit base. So already base can be larger than what could be accessed originally by real mode segments, because real mode segments effectively gave us 20 bits of addressing space. And here we have 24 bits. So within this 24-bit addressing space, we could define segment anywhere with any size by specifying limit. And here are some additional attributes. We are going to take a look at them later. And this is just padding to 8 bytes. Alright, let's look at the instruction that should allow to set the table. This time this is register loaded from the 6 bytes. But the last byte is ignored, so only 5 bytes are used really. And again, the first word is limit, and then next 3 bytes are base. And the last byte is ignored. And this looks very similar to what the descriptor looked like. Let's take another look at descriptor. First word is limit, and then 1, 2, 3 bytes for base. Therefore, this descriptor table defining register has format that is in fact the same format as this descriptor, but without these additional bytes. This byte is ignored, and this is not even present. This is a nice design because this allows to have a descriptor defining segment of containing the table of descriptors, and you would not need to define additional variable to load into descriptor register. You could just use the values already existing in descriptor, because descriptor register has the same format but only looks at initial 5 bytes. Let's start setting this up. So if we want to define input for LGDT instruction, and first word should be limit, and limit is the address of the last byte, so this is the size -1. This is going to be number of descriptors. Let's write it down this way. Times 8 minus 1. Each descriptor is 8 bytes. And then 3 bytes defining the base address. We are using FASMG now, so we could use an instruction like this to define number on 3 bytes. But because our COM program in DOS is going to be loaded at an address that is unknown to us right now, we are going to know it only at runtime. We need to set up these fields ourselves anyway. So, because we do not know this address, we will need to zero this field, and instead we can just leave it like that, undefined for now. Similarly, for all descriptors that we need to set up, we are going to have to fill them with right addresses that are known at this time. So perhaps we should write down some simple routine to calculate the base address to put there. Or even better, let's write a routine that would set up both base and limit. And we can keep this uninitialized completely and then set it up here. Let's say that we are going to have this prepared for storing this address. CX is going to be the limit, so we can take CX, immediately store it at VI, and then we need lower bytes of the base. What we know in COM is segment and offset in real mode, so we should perhaps be able to convert such address into a physical address to put in Descriptor. Segment. Well, we may want to put any segment there, so let's use general registers for this. So then to calculate the lower word of base, the segments have overlap, so we need to take the segment, shift it right, no, this one we are shifting left and we are adding the offset, and this is going to be the lower part, while the upper part we need to add with carry. Yeah, this should do it. And the final byte, because the base is defined on 3 bytes, 24-bit address. Oh. This should be shift right, my mistake. Yeah, the original DOS segment offset address is effectively 20-bit. So we have 16 bits in the lower part, and the upper part is the remaining 4 bits. So we shift it down so that only the most significant 4 bits remain. And now we can set up this descriptor. Well, this is not really a descriptor, this is just a global descriptor table register. But this function works just as well for regular descriptors as for this register, because the layout is the same. The difference is that descriptor has more bytes, but they are after this initial portion that has limit and base. So this is going to be number of descriptors times 8 minus 1 limit. As for the base, let's use our segment and offset within this segment. Is that more or less clear? So let's now prepare the actual descriptor table. So this should be this address, the address of actual table. The first descriptor is null descriptor. And we are going to need a code segment for our code. We are going to need some data segments for accessing our data. And for initial test, I'm also going to set up video segment to access some video memory so that we can see results. Therefore, we set up 4 descriptors. Perhaps I can write this down. We should keep track of our selector numbers. And this routine allows us to set up base and limit, but we also need to have the right attributes in these descriptors. So let's take a look at descriptor attributes. Here we have just this byte of attributes shown for code and data segment. Present is a bit that indicates that segment is present in memory. So obviously we need to set it up to 1 here. Descriptor privilege level. This we are going to cover this later in detail. For now we are going to set privilege level of everything to 0. 0 is the highest privilege. This bit indicates that this is a segment descriptor. There are also other kinds of descriptors. And this bit is 1 for code and 0 for data. So this indicates that this is executable segment here. This is not important right now. And this bit tells that code segment is going to be readable. It can be readable or not. It can be purely executable. For data segment, the same bit tells that data can be writable. And this final bit is not set up by us, but is set up by CPU when segment is accessed. Therefore we need 10011 and perhaps here 1 2 010. This is 9A in hex, and this is for code segment. And this is 6th byte. So here we have 2 bytes, 2 bytes. This is 5th and 6th. So to prepare the attributes, we need to fill them this way. And now for the data segment. Similar, but this should be 0. And just like we have said that code should be readable, then leaving the same bit on, data should be writable. So we just modify a single bit. So this is going to be 1001. Yes, so this should be 9.2. We have attributes prepared. Now we need to prepare addresses. So this time we set up fields in the descriptor table. First code. Limit of code, let's set up the same segment that we have here in real mode. So CS starting from offset 0. This should mirror code segment that we are using in real mode. For video segment, well, let's set up some non-text mode. Text mode use video memory at segment 0b88 B800. This is physical address multiplied by 16, so additional hexadecimal digit. Well, this time we can set up smaller limit. This text mode is 80 times 25. 2 bytes for every character. -1 because limit is the address of the last byte. This had set up a video descriptor. What remains is the data descriptor. Let's create some data here. Let's have some message to display. So now we can set up data segment so that it encompasses only this data here and nothing more. In protected mode, segments can be much smaller than 64 kilobytes. -1. This is the same segment, or we can use DS here, but this is the same as CS in case of COM program. And offset is data. Great, we have set up all bases and limits. For descriptor table register and then for descriptors within the table. We should disable interrupts because for now we are not going to have them set up, so they would not work. An interrupt would crash the machine. And now, to enter protected mode, we need to use some additional instructions. We need to modify something that is called machine status word. So we first store value of this machine status into AX register. We modify it by setting up the lowest bit. This lowest bit is just protected mode enabled bit. And we load the register, this value of register into machine status word. After we entered protected mode, oh, what should happen? Note that all our registers, including segment registers, are still as they were before, so this should probably crash, one would think. But there is another interesting detail of this architecture. That inside CPU, next to the visible selectors in each register, CS, DS, ES, SS, there is a hidden descriptor. And this hidden descriptor is not updated until a new value is loaded into this register. So in real mode, this hidden descriptor is set up in such way that it all works in a compatible way with previous CPUs. And therefore, until we change one of segment registers, this hidden descriptor continues to work as before, as in real mode. So we are safe to execute some additional instructions before everything crashes. So code segment is going to be executed as before until we change it. And we are going to change it with jump far. Selector for code is 1. The lower bits can be zeroed for now, because we are using global table, so table indicator should be 0, and privilege level, as I said earlier, we are going to have 0 everywhere. And let's jump to label that is going to our protected mode entry. Now let's say here. We have set limit for code to be 64 kilos, so we have full segment available for execution. Now we would like to write to video memory. So let's set up ES register with video selector, which is 3 times 8. And let's set up DS with our data selector. We are going to copy the message into video memory, but every character in video memory is 2 bytes. Second byte is attribute, color. So let's prepare some color. This should be blue background, gray text. This in a loop how many times, how many characters. Well, let's for now just take entire data content. And then let's just halt. We have interrupt flag cleared here. So with no interrupts enabled, halt should just hang forever. Well, unless in NMI happens, but that's another story. Well, should we try if it works? It assembles. But does not run properly. We have a bug somewhere. Let's check this routine. This should be added. I'm adding the offset. And of course then I'm adding with carry. I have just written instruction. Not the instruction I meant here. It worked this time. We are entering 16-bit protected mode of 286 processor.